Mazal Tov, David. I first met David probably about 40 years ago, I think, something like that. We met actually in Cornell and later on in the Institute of Advanced Study. And we actually started to collaborate right away. And as anybody here who collaborated with David, I can also witness that it's really a very stimulating and rewarding thing. And we collaborated then and continue to collaborate when I joined the School of Physics of Tel Aviv University. So happy birthday, David. Okay, we arrived to the last session of the Hornfest Symposium, and following the previous session, also this session will reflect on topics, issues that David worked on and was interested in during his long and very successful and fruitful career. The first talk will be by Gabriele Veneziano from CERN, École Normale, and I think now also from Rome, right? Or Collège de France, sorry, and I think also from Rome. Gabriele, for a lot of us, needs no introduction. He is a very renowned physicist with a lot of really great achievements. He got several awards and medals like the Pomeranchuk Award, the Hyman Award, the Einstein Medal, and the Oscar Klein Medal. Gabriele did his PhD here in Israel, and I think you first met David when David returned to Israel, and you were still a postdoc, a PhD student at the Weizmann Institute. And when David came to Israel, he, together with Chaim Harari, established the famous joint seminar, which this year we are going to celebrate its 50th year. And I think that probably Gabriele was among the participants in the first joint seminar. And the famous work of that Gabriele did just after finishing his PhD here in Israel about the so-called Veneziano amplitude that later on led to string theory. It was actually very much influenced by the very well-known work of Dollenhorn-Schmidt on duality and finite energy summary. So we are very happy to have Gabriele here with us, and Gabriele will talk on quantum universe before the Big Bang. Please, Gabriele. Yes, this you put on your photos, on your phone, and you all this.
Okay, thank you very much. And well, it's a great pleasure and honor also for me to give this talk to celebrate a dear friend and esteemed colleague. As Shimon was saying, I did my PhD at the Weizmann Institute, and indeed I met for the first time, I believe, David 50-some years ago, when he returned from Caltech, and I was just finishing my PhD. Now, the reason why you see there the Tel Aviv University in my affiliation is that this is my present job, because I retired from CERN and from Collège de France, but still have a Sackler chair. You see, both David and I started in practical physics. As Shimon recalled, we were working in very, very closely related subjects. Now, later on in my life, I moved to some other areas, but unlike unlike David, I stayed within physics, okay? But for me was quite... L'Ozzet? L'Ozzet. Can? So I would like to start with a couple of... Shimon already mentioned this, but repetita iuvant, so I will go through it again. Well, first of all, I would like to say that I was a participant in the previous edition 20 years ago, you see October 97, where I will blow up a little bit. I gave a talk indeed about the work of David and its later development. And well, I could have chosen a very similar topic for my talk today, because this STU duality that David introduced led to further developments. In fact, in 97, in December 90, end of 97, Juan Maldacena introduced the ADS-CFT correspondence, which you can call a gauge-gravity duality. So even that further development, which is still occupying many, many theories today, had to do, in a sense, with David's work, because it's related to duality between closed and open strings. It's a slight generalization of what they did at the time. Now, the second historical preamble was indeed about 50 years ago. 50 years ago, in 1967, this is my own account of the story. Of course, it's my personal view of it, my personal experience. For me, the shock came when I was, as a young student, at a summer school in Erice in July 67, and I heard a talk by Mary Gelman, which was bringing news of a small, let's say, it looked small, breakthrough. This was the work of Dollenhorn and Schmidt, saying that two apparently distinct contributions to some strong interaction processes, which previously were thought to be unrelated, were actually strongly related. And adding those two contributions would lead to a double counting mistake or sin, even. And this opened the way to the correct use of certain sum rules and to what Gelman called a cheap bootstrap, in contrast to what was prevailing at the time was the original bootstrap formulation of Jeff Chu. In fact, Jeff Chu's original bootstrap was making crucial use of a nonlinear constraint called the unitarity constraint. I remind you that in quantum mechanics, probabilities are related to absolute squares, so nonlinear. And this made his program a very and perhaps too ambitious one. Now, I learned just 2 days ago from David that Jeff Chu immediately understood the importance of Dollenhorn-Schmidt duality as a linear, like a nonlinear bootstrap constraint, and predicted that it would lead to many further important developments. There is this article that he showed me. Now, in fact, this duality deeply influenced subsequent work done mainly in Israel by Ademollo, Rubinstein, Virasoro, and myself, plus two young students, Bisharin and Schwimmer, and this culminated in a so-called beta function solution of the bootstrap and eventually to string theory. Now, it turned out that that string theory that one found at the time was not the correct theory for what it was invented for the strong interactions. But I think Dollenhorn-Schmidt duality survived even that because it's believed to be a property of the correct theory of strong interaction, which is QCD, provided one does a particular expansion of the theory. And this is certainly, by the way, in my opinion, one reason why string theory was discovered by trying to model the strong interactions using the duality idea of Dolan-Hornsby. Now, I have to switch gears and talk about a completely different subject on which I don't think David has worked, but hopefully maybe he will, he will join in later. Who knows? We are in for surprises. So this is the outline of what I will be talking about. First of all, I will now jump again 50 years in the future, namely today, and say a few words about what is our standard model of nature today. But then I will quickly concentrate not on elementary particles, but on gravity. And first I will talk about classical gravity, and then, as you have seen in the title of my talk, I will try to stress the importance of quantum mechanics in modern cosmology. By the way, I will be talking about the first billion years of the universe. You heard already about the remaining 12.5 billions. And then, okay, the importance of quantum mechanics, and then I will ask the question, which Big Bang? I think up to there, things will be pretty straightforward and hopefully uncontroversial. From there on, which quantum gravity, string theory, and cosmology, it will be much more of a speculation and try to conclude. So the standard model of nature, as we know it today, is based on two pillars. There is a quantum, underlined quantum, gauge theory of elementary particles and of their non-gravitational interactions. And the word quantum is absolutely essential. Without quantum corrections, the theory doesn't fit the data by many, many standard deviations. And then there is a classical general covariant theory for the gravitational interaction, which is nothing but Einstein's general relativity. Now, so leaving aside elementary particles for reasons of time, let's focus on the standard model of classical gravity, general relativity, whose starting point is the equivalence principle embodied in the universality of free fall, something which is extremely well verified, and then which is also well verified at some corrections to Newtonian gravity. This is a plot of how from the times of Galileo until today we improved our precision of the universality of free fall, on which really general relativity is based physically, of course, and there is a whole mathematical construction behind it. The new predictions that general relativity does are, as we heard today, black holes for which there is direct evidence. For instance, this is a picture of which was also shown this morning about the black hole in the center of the Milky Way, and more recently gravitational waves, for which we had already indirect evidence, but since last year, there is direct evidence, and we had a Nobel Prize this year. As of this summer, also Virgo is operating. This allows to improve source localization. There was a triple observation last August. And this, by the way, includes new evidence for black holes. Great, important development. And as you heard probably in the news, on October 16, a few days ago, there was the first observation of a neutron star merger with simultaneous gravitational wave and electromagnetic emission. I will skip this thing because, well, these are for lack of time. We have seen that already in the previous talk. So what I want to stress is that up to here, nothing but classical gravity is involved. You can take Planck constant, put it to 0, and nothing would change. But I claim is that things change as soon as you apply general relativity to early cosmology. However, okay, quantum mechanics was invented much before, and things didn't change for a while. So in fact, before the 80s, there was some kind of classical dogma that, you know, everybody, even perhaps people in the street, know the hot Big Bang scenario, according to which the universe was born together with time itself about 13.5 billion years ago in a state of extremely high temperature and density. And if you try to go beyond the singularity, which means simply that certain physical quantities become infinite, prevents us from going beyond such a moment in our past. And then since then, an adiabatic expansion, very rapid initially, then slower and slower, cooled down the universe. And we see traces of that in the cosmic microwave background, which is, you know, permeates the universe and has a temperature today of about 3 degrees Kelvin. However, that hot Big Bang scenario leads to strong puzzles. I will enumerate 3 of them. There is an homogeneity problem, the fact that the universe is very homogeneous and isotropic on large scales, in the sense that the CMB temperature varies only by 1 part in 100,000, depending on the direction it is coming from. And this property has to be put by hand as an initial condition in this hot Big Bang scenario. In fact, if we start from more generic initial conditions, and the expansion has always been of this decelerating kind, as it used to be, the observable universe has always been too big for its age to be able to get homogenized since the beginning of time. So this I illustrate typically in such a figure where we are here today. By definition, our observable universe is as big as how much light has traveled since the Big Bang. But if you go back to your past, then you see that because of this decelerating expansion of the universe we observe today was bigger than the red ellipse, which is how far light could have propagated at that time from the Big Bang. And because of this difference in size, it's very hard to understand how the whole universe could become homogeneous. Now, there are other puzzles. One is called the flatness problem, which means why the energy density of the universe is so critical, is so close to the critical one. I would not explain exactly why, but there is a similar fine-tuning issue associated with that puzzle. But I would like rather to concentrate on the fact that in the universe there is a lot of structure. There are galaxies, clusters of galaxies, and substructures of galaxies, stars, and so on. And in order to get that structure today, you have, again, to start with an extremely highly fine-tuned Big Bang. There is either too much structure or none at all. So if you put no inhomogeneity in the beginning, you don't generate any inhomogeneity. If you put a little bit too much, you generate too much structure. So all these problems are related, as people understand in the 80s, to 2 things: the existence of the beginning of time, but also to the fact that the expansion of the universe is decelerating. And if instead of having a decelerated expansion all the time, In the primordial universe, there was a phase of accelerated expansion, then you can solve the homogeneity and flatness problem very easily. I will discuss just in a moment the structure problem. Because the universe, I mean, you can, rather than reading the sentence, you can look at my previous diagrams. If you insert in the early history of the universe a period of accelerated expansion, which means that you see the curve, the blue curve is convex for some time and then becomes concave. Then immediately you see that now the blue ellipse can sit well inside the red one, which means that the universe was small enough at the beginning that it could get homogenized. And then, of course, it blew up very large, but this homogeneity will persist. So this gave rise to what we can say the standard model of cosmology today. It puts together this inflationary scenario with the observation that the universe has also a dark sector, a dark matter, and a dark energy sector in the budget of the universe. Again, no time to go into details about that, but I'm pretty sure you have heard this story. Now, the importance of quantum mechanics in cosmology. This is the punchline. Namely, suppose I have inflation, but I am in classical physics, no quantum mechanics. Then you can show inflation produces a perfectly homogeneous universe. Why? Because even if you start with some initial inhomogeneities, these are stretched and practically erased from us. The expansion is so huge that every wavelength is stretched and today will be bigger than any scale we can observe in the sky. So inflation classically is very efficient for erasing inhomogeneities. With quantum mechanics, so there is no way to form structures. Now, quantum mechanics does the same in the sense that it does exactly the same for the initial inhomogeneities that could have been there at the beginning of inflation, but since you cannot turn off quantum mechanics, okay, quantum mechanics replaces the initial inhomogeneities by calculable quantum fluctuations, which are produced, amplified, and stretched, not at the beginning, but throughout the inflationary epoch. So those which were produced late enough during inflation will still be inside our horizon today and will represent the structures we see in the sky. You know, it's a mind-blowing concept to think that all the structure we see in the sky is nothing but some original quantum fluctuation, amplified and stretched. So the CMB, the cosmic microwave background we observe today, carries an imprint of those primordial quantum fluctuations. And this is famous plot of Planck, which plots the temperature fluctuations in the sky as a function of the angular scale. And of course, there are parameters in the fit, but the agreement is really very impressive. This is not the only place where quantum mechanics plays an important role in cosmology, because inflation is an adiabatic expansion, and as the usual expansion of the universe cools it down. And since it's a very, very big expansion, it cools down the universe practically to zero temperature. Now, can we generate a hot Big Bang after inflation? We need it, because if there is no hot universe at some time in our past, we will have no cosmic microwave background. There is no Big Bang nucleosynthesis, the synthesis of the light elements. Note that in this inflationary scenario, the universe is expanding all the time. First in an accelerated way, then in a decelerated way, but it's still expanding. So where does the hot Big Bang come from? It comes from a second intervention of quantum mechanics. They are dissipative, non-adiabatic conversion of potential energy into a hot thermal soup of elementary particles. In jargon, this is called reheating the universe after inflation. And it's a very quantum mechanical process. Now, this is, you see, I put in a frame because I think it's perhaps the most important message which I want to convey. Physically, reheating plays the role of the old hot Big Bang. You say, where is the Big Bang in the inflationary scenario? It is the reheating of the universe at the end of inflation. Therefore, it is, but it is not singular because, okay, you reheat the universe from 0 temperature to some temperature, certainly not to an infinite one. So there is no singularity associated with this Big Bang. And, of course, since it's at the end of inflation, it's certainly not the beginning of time. So there is a redefinition of what the Big Bang is if you believe in this inflationary paradigm. So, but, okay, we keep telling people, to the general public, the Big Bang is the beginning of time. And you see, according to inflationary cosmology, we have somehow to distinguish two concepts. There is a physical, non-singular Big Bang at the end of inflation that left measurable relics, the CMB, Big Bang nucleosynthesis, many other things, which we care about and we can measure. So that's why I call it the physical Big Bang. Then there is another question. There is a theoretical Big Bang, which could be singular, could not be singular. They could have preceded inflation. Could. But nobody knows. Okay? Or rather, this is another question which we will try to address in the following, but for which we have no answer. So in any case, the Big Bang we know something about has nothing to do with the beginning of time, I pretend. So, you see, but still people show these pictures. You see, Big Bang, inflation. Wrong. Okay? In my opinion, this is completely misleading. Inflation is actually quite agnostic about what happened before it started. Of course, we would like to know how it started, but that's a separate issue. So Big Bang should be put here. You see, when you end inflation, the universe reheats, and then the history from here on. So when people tell you so many seconds after the Big Bang, they usually refer to so many seconds after this point. Of course, if you measure things in seconds, it doesn't matter because all this lasts a very, very, very tiny fraction of a second. So it will not change the numbers. But, you know, in general relativity, you should be very careful about what you call time, and you can redefine time. For instance, talk about redshift instead of time will make that period much, much longer. Okay, so first conclusion, a necessarily quantum cosmology, in my opinion, before and during the physical Bang. It was quantum mechanical during this reheating period, and it had quantum mechanics all the way before reheating, during inflation, in order to produce the fluctuations and the inhomogeneities which gave rise eventually to the structures we have in the sky. Then, second and last part of the talk, what about truly the beginning of time? Now, we don't know the answer to that question. As I said, inflation is very agnostic about that, but clearly the answer depends on another question, namely, which is the correct quantum theory of gravity? Since I argued that you need quantum mechanics in inflation, if you want to answer an even deeper question, the beginning of inflation, you need to have a quantum theory of gravity and solve it, unfortunately, too. Now, by the way, cosmological perturbations, which I briefly discussed, can be treated without a full theory of quantum gravity. You do some kind of semi-classical treatment, and this is sufficient. Now, but how to quantize gravity? This is a notoriously difficult problem. The most interesting attempts to these days are those of loop quantum. How to quantize general relativity? Yeah. I call loop quantum gravity, and there is another approach called asymptotic safety. I have no time, of course, to talk about those. But the important thing is that they both assume that one can make sense of quantum gravity by modifying the way to quantize general relativity, but not by modifying the starting point, okay? Now, this could work, who knows? I have my own reservation based on a lesson we learned in particle physics. You know, in the old days, there was a Fermi theory of beta decay, the neutron that decays into a proton, an electron, and a neutrino. And today, it is replaced by a more complicated picture. The neutron is composite, the proton is composite of quarks. But most important for this talk is that the vertex at which the neutron turns into a proton and the vertex at which an electron and an antineutrino are created are not the same point in space-time. So the interaction, which here in Fermi's theory happened at one point, is mirrored in the Glashow-Weinberg-Salam theory, which is the standard model that we have today. So it was not a matter of finding a smart trick to quantize Fermi's theory. We had to modify Fermi's theory, and in particular to soften the theory. Okay, this theory is softer. It doesn't. Okay. Now, and then there is a second lesson for particle physics that I would like to bring up. According to our present understanding of fundamental interactions, they are all transmitted by massless particles at some deep level, by some massless particle of spin 1 or 2. For instance, the photon will give rise, the existence of a photon will give rise to non-gravitational interactions, in this case electromagnetic, while a graviton, which is a spin 2 massless particle, is responsible for gravity. In fact, you can argue that both the gauge invariance and the general covariance principles, which are usually at the basis of the description of these two kinds of interactions, follow from the consistency of the interaction of such massless particles. I mean, strictly speaking, this gauge invariance is very important to remove some unphysical degrees of freedom that massless spinning particles do not have, okay? You may know that a massless particle has two polarizations. A massless spin 1 particle or spin 2 particle has two physical polarizations, where if they were massive, one will have 3 polarizations, the other will have 5. You have to remove this unphysical polarization, and the gauge invariance and general covariance do precisely that. So I'm trying to argue that perhaps you should take a revolutionary attitude that general relativity and also gauge theories are a consequence of quantum mechanics. So you don't try to start from a classical theory and quantize it. You want to see the classical theories themselves to emerge in some limit starting from quantum mechanics. Now, this looks like just words, but I will argue in the rest of the talk that this is really what string theory suggests, okay? Is what string theory seems to implement, precisely this thing. So, how much time? Yeah, okay, I'll try to tell you all about string theory in 2 minutes. So, you see, what is string theory? String theory is the theory of strings. So, what it means by this kind of joke is that you replace ground principles, as I said, you start with gauge invariance, general covariance, the geometry of space-time, which is the Einstein theory, just with a very innocent-looking assumption that everything is made of relativistic quantum strings. Okay, so you say there is relativity, there is quantum mechanics, and then the extra ingredient you have to accept is that the most elementary objects are strings. Okay, so strings come in two kinds: open strings, closed strings. Okay, you take these three things together, you shake well, and you get a very interesting cocktail. Because something magic emerges from quantum mechanics. For instance, if you take a classical string with a tension T, it can have any size and any mass, because the mass is proportional to its length. You take a short string, it will be very light. A long string will be very heavy. But there is no intrinsic scale in the problem. But if you introduce quantum mechanics, you find that there is a minimal optimal size for the string, and therefore also characteristic scale for its mass. The analogy again with something we know already, atoms. You know, a classical atoms would be unstable. The electron would fall into the nucleus. But quantum mechanics tells us that the electron sits in some orbit. Of course, it's fuzzy, but sits in a state in which the atom has some size. Now, now what happens? As a result of this intrinsic size of my strings, the interactions among strings is softer than the interaction among point-like particles. Point-like particles like to interact at a point in space and time, but strings, you know, you cannot find here a particular point where they interact. It's a whole surface, and which changes topology, by the way. And so interactions are smeared over regions of order of this fundamental length scale, which, by the way, I forgot to emphasize, contains the Planck constant. Okay, you form a length scale using the tension and the Planck constant, very similar to the Planck length. Now there is this smearing of the interaction is what cures the ultraviolet problems of conventional quantum gravity by actually removing ultraviolet divergences altogether. It's not just that you make the theory a little bit softer. Here you just remove the ultraviolet problem. Remember that Planck invented the Planck constant to solve an ultraviolet problem in black body radiation. Here, it's a bit similar. Now, the second magic, there are more, but I will limit myself to two, is that classical string cannot have angular momentum without having also a finite size. You can imagine, okay, if you want angular momentum, you have to have some extension. If you have extension, you have mass, classically. But quantum mechanics is very smart and manages to upset a little bit the classical inequality, which would prevent J from being non-zero for a massless particle, and it prevents it by exactly the right amount to allow for possible spinning strings of zero mass and angular momentum up to 2, up to spin 2 in units of h bar. So here comes our Copernican revolution, because string theory gives automatically, and in fact this was a death sentence, by the way, for the old string, okay, that didn't work for strong interaction, because it produced it insisted on having in its spectrum a massless spin 0 or several massless spin 1 massless particle and a spin 2 massless closed string, the graviton. So, and then, not surprisingly, when you look at the interactions among strings, you find that among these interactions there are gauge interactions and there are gravitational interactions. And since all elementary particles in this theory correspond to different vibrations of one and the same object, or two objects, open and closed strings, no miracle, no surprise that all these interactions get unified among themselves. In fact, they have this geometrical origin that I showed in this picture. So, combining both miracles, it provides a unified and finite theory of elementary particles and of their interaction, which is based on quantum mechanics. And quantum mechanics gives directly quantum versions of Maxwell theory, Einstein's theory, and the classical limit is recovered in some approximation. However, because of this finite extension of the strings, it also provides automatically short distance corrections and removing therefore these bad divergences. I think my time is off, so probably I will only go very, very briefly back to this question of the beginning of time. The point is, what answer can possibly string theory give, if it is the correct theory, we don't know, to the question of the beginning. And you see, string theory implies modifications of general relativity when the curvature of the geometry becomes comparable to this quantum length, this L, this minimal string size. And that almost certainly gives an upper limit to density, temperature, curvatures, and so on. So I think the majority of string theories would agree that there is no place for the singular Big Bang of classical cosmology, but the big question is what replaces it. And I will end up mentioning just the two possibilities that seem to be most likely. One is that the cosmology has a beginning which is not classical at all, and that the usual concept of space and time spring out of that phase as emerging concepts. It's a little bit close in spirit to Hawking's no boundary idea. So my previous diagram will be replaced by something like this, where there is a new phase which you cannot really describe in terms of the usual geometry. And the other possibility is that it's a cosmology without a beginning period. Namely, there is really no beginning whatsoever, and in that case there could be a quantum string phase making a bridge between a previous classical and our cosmology. Now, the difference between the two scenarios is, well, if we concentrate for a moment about this one, just not to waste too much time, there are two possibilities still, that this pre-bounce phase could either prepare or just replace completely the inflationary scenario. Now, in the first case, it could answer some outstanding questions about initial conditions in conventional inflation. How did inflation start? This is still a big mystery. if you had a model of what happened before, then you may understand why and how inflation started. However, in that case, inflation, as I told you at the beginning, washes out a lot of what was before. That's why it makes robust predictions. And therefore, what happened before will be screened from ever from observation. In the latter case, in which this bound replaces the inflationary scenario, you could have observable consequences, and people have worked out several of them. For instance, a very distinctive prediction of this scenario is that there shouldn't be any primordial depolarization in the CMB. You know, people have been looking for it. There were claims that they had found it. Then the claims have been taken back. So this scenario is still alive. Okay, I think I conclude by repeating myself. Classical general relativity works very well in a large number of situations. However, for cosmological applications, in particular in the inflationary scenario, general relativity needs quantum mechanics. Quantum mechanics is at the origin of the large-scale structures in the universe. It is also necessary to reheat the universe at the end of inflation. And I stress that that moment of reheating is really what plays the role of the traditional Big Bang and has nothing to do with the beginning of time. We don't know what started inflation, and to answer that question requires to have a good theory of quantum gravity. If I look at that particular theory, which is called string theory, then the classical Big Bang singularity should almost certainly be avoided. The question of the beginning is well posed, but I don't think we have a solution to it. Well, in Italian we say there is no two without three, so we are looking forward for the next Hornfest. In Hebrew you say ad mea esrim, so there is even a room for a fourth. Happy birthday, David.
Gabriele, we had earlier today a beautiful talk by Hagai Netzer about black holes.
Yes.
And in the end of your talk, you pointed out that this mechanism might resolve the issue of cosmic singularity, cosmological singularity.
Yes.
So do you have any favorite speculations about how this technology could resolve the singularities associated with black holes?
Well, yeah, well, of course, you are perfectly right. So I remind people that the classical theory of cosmology and of black holes, has singularities. One is the Big Bang singularity. The other singularity is what you find inside the horizon of the black hole. Okay, for instance, the Schwarzschild solution that we have seen. So, and the two things are very much related because, okay, people who know general relativity know that actually the geometry inside the horizon of the black hole, it's a cosmological type of metric, of geometry. In other words, the center of a black hole is not like the center of Earth, a point in space. It's more like a point in time. Okay? There is a big crunch inside. So, if you want, black holes are like big crunches, and our cosmology is a Big Bang. Okay? Initial or final singularities. So, indeed, there is a lot of interest. In fact, I myself have been working in both fronts. And for instance, one thing which I can answer, but is by far not exhaustive, is that there is a little problem. People have probably heard about the Hawking radiation, which says that a black hole is not, after all, black because it emits radiation in the thermal radiation. So if you leave it in isolation, a black hole, instead of accreting stuff from the outside, it will slowly evaporate. Okay, this is a well-known Hawking process. Now, what happens at the end of this evaporation? In the standard picture without strings, we don't know because the temperature grows as it evaporates. The temperature is inversely proportional to the mass of the black hole. So as the black hole becomes smaller and smaller, it becomes hotter and hotter until, again, you hit the singularity, very much like the Big Bang, infinite temperature. Now, in string theory, that we know pretty sure, as it shrinks its size, the black hole arrives at some point to be of a string length size, my LS, and at that point it will no longer be a black hole because its size will be bigger than its Schwarzschild radius. So it will behave like the sun, like the Earth, we heard this morning, a few millimeters and so on. We are not a black hole, the sun is not a black hole. The same way the black hole will shrink, but by the time its Schwarzschild radius becomes of LS, so this has been pointed out in papers and so on. So the evaporation of a black hole is not singular in string theory. And my belief is that understanding how to remove the singularity will also shed light on the so-called information paradox, on which I don't want to enter now.